Hey guys, my name is Rian. I'm Brazilian. Right now, I'm finishing my degree in computer engineering, and I'm also participating in Cartesi DVAD seed grants with my team. We are called the Prism, and our idea is to run decentralized stable diffusion models in the Cartesi machine. Our product is that we create t-shirts with a design made by the customer by a prompt, for instance. Um, but right now, I intend with this video to explain a little bit outside of the Prism environment. So I will not be showing you the t-shirts, nothing, none of that. My idea here is to make a video summing up our development, trying to run the stable diffusion model in the Cortez machine. So this will be the focus of this video. Um, and well, we have been trying to do this in the last few months. So we started our journey with Python. We are trying to use PyTorch and conventional, let's say, models, ways of achieving this goal. That is to run the stable diffusion model. But it was too resource consuming, the PyTorch, and we had a little bit of problems with the RISC-V architecture also. And um, in the last few weeks or even months, we changed the way we were doing things, and we come up to have better results with this that I'm going to show you right now. That is how we are doing things now. Uh, we achieved some pretty satisfactory results. Of course, that is not perfect because we are trying to run a stable diffusion, a huge model in the Cortez machine that is a RISC-V architecture. We have our limitations. We are actually trying to, in some way, push the edge of this technology. We're trying to make a show off of what is possible in the future with the improvements that the Cortez team is making, the Cortez machine. So this is the idea. So with no further ado, let's go to the code, right? Just a quick reminder that this is intended to be a pretty informal video just for the ones that are interested on how we did things. So if you see us doing something that could be better, or if you have any suggestions on how we can improve things, please leave a comment or call us. I will leave my links in the description, so if you want to reach me, you can do that also. And well, this is it. Let's go to the code. First of all, I would like to show you this repository that is one of the bases that we are using in our code. This is made by, let me see here, the author of this code. I believe maybe this is in front. Liget, stable diffusion in C++. So this is the first thing that I would like to explain, that we changed to this implementation of the stable diffusion in pure C and C++. One of the reasons is that we are using a RISC-V architecture that is CPU only, right? So we come up to achieve significant better results with this implementation that we had achieved with PyTorch, with Python and PyTorch. But I would like to mention that we did our code in C and C++, but you do not necessarily need to use the app code in C or C++ just because the implementation of this implementation of the stable diffusion is in C or C++. I will make this clear for you when I show you the code of the Cortez machine. But for now, I would just like to explain to you better a little bit about this repository. What we are looking here with this code. This implementation, you can think of this like an executor for the stable diffusion models. So what we achieve when we follow the instructions here of this repo and all of that is that we get a binary that is able to execute the stable diffusion models. So we need, for instance, to have a model downloaded, we have to give the prompt, all of that. So what we get with this is a binary. And of course, that in the way that is implemented here, if I build this binary in my machine, that you can see that is a MacBook, this binary will only be able to execute the models in the Mac OS environment. So this was one of the first challenges that we had. So we used an emulator of RISC-V to generate a binary for the RISC-V architecture, and in this way we are able to run the Stable Diffusion model in the Cortez machine with the RISC-V architecture. So this was one of the first achievements that we were able to make. And well, just to show you, we use this prompt style to run the model. I will make this clear for you. But for generating image beyond the size here, with GPU only, we consume with the model we are using like 2 gigas of RAM. That is not much for what we are trying to achieve. We could have used this flash attention, but I had some problems. I'm not sure if the implementation of this is already finished by the people who are maintaining this code. Had some trouble with that. I believe it could be a good thing, but for now we are using the standard built binary, and it's working fine. So this is it about this repository that I want to discuss with you. You can check this better for the parameters if you want to understand which of these are doing. But let's go for the code. Let me put my camera here. Maybe in this corner is better, right? So this is the code that we did. Just let me explain to you a little bit about what we have here in the VS Code, the files that we are dealing with. So as I told you, this is a C++ implementation that I did here, but it not necessarily needs to be C++, because when we download this repository that I just showed you, we compile this binary here. We build this binary. You can see that I have two. One built for Mac and the other one built for RISC-V. So this binary, it is what is responsible for executing the Stable Diffusion model. So this is the only thing that I need. So you can see here, I don't have anything else about this repository. You can see that it's a lot of files. I don't have none of this here. I just have the binary. Also, I'm using this model fine-tuned of the Stable Diffusion. I'm not sure about the name right now. I changed it here because it's a model that generates pixel art. I choose this one because it was a little bit lighter, and as you will see, it takes a little bit of time to generate an image in the Cortez machine as we have this code right now. But I will for sure let all this in the comments so you can check this better. But you could use the conventional 1.5, 2. Version 2, or I believe right now we have version 3, right, of the Stable Diffusion. You can use the standard models, or you can use a fine-tuned model. It's all fine because this binary is able to execute any model that you want. But if you use the latest model, for example, maybe you will consume a little more space on the Cortez machine, a little more RAM. So this all needs to be taken in consideration because of the limitations that we have right now with the machine. Um, but uh, beside that, I have here the implementation of the app is a pretty standard implementation, right? I will not be enter this in detail because I will leave this code in a GitHub repository so you can check this out for yourself. But it's a pretty standard. We receive a advanced request. In this advanced request, we receive the prompt as a parameter with, I will show you this to you. But the idea is that when we receive this advanced request, we run the command for this binary to generate our image for us. And when the image is ready, um, we encode the image in the base 64, and with this base 64 we convert this to hexadecimal so we can send a report in the Cortez ecosystem, and with this report that contains the base 64, we can generate the image later as it is convenient for us with a base 64 to PNG or anything the way that you want to deal with your image, right? Um, but this repository, as you are seeing, is nothing to deal with the Prism or anything like that. It's a research and development repository that is only intended for us to explore running stable, decentralized stable diffusion models, right? So I believe maybe this part of this code is a little bit clear for you right now, all right? Um, and exploring a little more about the Docker file. So the Docker file is when we built the image to run in the Cortez machine. So you can see here that when we are running this with Docker, we have all these containers, and it has some difference between running things in our terminal and running things in Docker with the containers, the volumes, and etc. First of all, just let me show you here. I let these parameters here because when we are running using NoNodal, for example, that is a tool of the Cortez that the Cortez team made for us to test our applications a little bit faster, we need to consider our environment. So in my case, Mac OS system. But when we are running in Docker, we have to consider the RISC-V architecture. So this is what we're doing here. You can see that the SD command that is part of the prompt that we are going to use to generate the image here that I'm considering running with NoNodal in my environment, I'm using SDMac. But when I'm using the running it from Docker, I'm using Opti Cartesi DAP SD. That if we go here in the Docker file, what is this? We copy SD RISC, that is SD for RISC-V, and put in this folder right here. So what we are saying with this parameter is that we want to use this SD-RISC version of the binary that executes the stable diffusion model, right? I believe this is clear right now for you. I will leave this to run in my Mac right now because running it in Docker is a little bit more difficult because it takes a little longer to generate images. I will try to show you the results I've achieved with my tests, but right now I will be using NoNodal just for the sake of this video, right? So just taking a deep dive in the Docker file, one change that we need to consider is the RAM size that we're going to use. Right now, I allocated uh, around 3 gigas of RAM. It's not exactly 3 gigas because you know about the binary and stuff. That is not exactly 3000, okay? But around 3 gigas. So this you will need to consider the model that you're using, the size of the image you are trying to generate. So this may change for you. But in my tests, this of course depends on the if you are running this locally on how many RAM you have available for running Docker. Um, of course, so I can make a general statement of this, but um, in my tests, I also discovered that when I use uh, a number that is a little bit high, I receive more errors when I try to initialize my Cortez machine. So I have 16 gigas available here. And for example, when I tried to use 8 in the Docker file, I had some problems. So I encourage you to test, of course, but if you're having problems, maybe not exaggerating in this value of RAM, okay? Um, and the other thing that we need here is the all the files that we are using to run. So of course, our DAP, our binary executor, right? Our model, we have to give permission to execute the binary. I have here a folder to keep the images that are being generated, giving some permission to this folder. And this is basically it. Not a big deal, right? Not many changes to the Docker file. Um, so the last piece of the puzzle is the Cartesian. When we use this .cartesi.env, we can actually change some values for some variables in the Cartesi machine, the code of the Cartesi rollups actually, and there are some that is also ecosystem dependent. So when I'm using my Mac, I have to use some values. When I'm using a Windows with WSL, maybe other values. This I say based on my tests. Of course, I'm no Cartesian machine expert or core developer, right? So of course I can be making mistakes on this. But in my tests, the most crucial environment variables that you must deal with is SM pending inputs sleep duration and SM pending inputs max retries. Okay, so as you can see here, I put a very high value in the max retries and a reasonable value for the sleep duration. Why we made these changes? Um, when we are trying to generate an image in the Cortez machine, it can actually take a pretty long time because we are using CPU only and a RISC-V architecture CPU that has its limitations. So we actually were trying to generate an image using a large artificial intelligence model. So you understand that we are trying to kill an elephant with an like a rock maybe. Um, so for example, trying to generate a simple image with not very high parameters of quality. For example, not many steps for the stable diffusion model, not the best quality of the world. We maybe take 50 hours to generate the image, like through 2 or 3 days, all day long. So we send this advanced request, and if we do not change these variables, this request will die, and we will have no answer for our request. The report will not be generated. So this is what we are setting with these variables. So our advanced request do not die because of the long time that will be taking for our image to be generated, or in other words, to this request have a response. So what we are saying here is like try this many times with this period between the times that you're trying. So I did not did the calculations here, but I believe I chose like one value that for sure would be fine. Uh, and the other ones is for initializing the machine, because when we for example type Cartesi build and Cartesi run, um, we are initializing a lot of services, and these services have their internal Docker compose that have this health checks and all of that good stuff that is made by the Cartesi team. But as they not did not intended to be like to have this huge files, this artificial intelligence models, maybe these extreme scenarios we have to make some changes so our Cortez machine can initialize. Okay, so the amount of time that the Cortez machine can wait for the services, for the advanced requests, for the check-in, and in this can actually change based on the ecosystem that you are using. So from my personal experience with these values, maybe when I type Cartesi run, it did not go in the first try, but I try again, and then it goes. Maybe you have to restart Docker or clean uh, the Docker storage that you are using, like a Docker prune. So you have to do this kind of stuff when you are dealing with such of an extreme case for the Cortez machine. Okay. Um, so these two, of course, is crucial. The inputs, pending inputs, max tries and sleep, and the other ones you have to try for yourself to run in your machine, in your ecosystem, right? Um, for the last thing, I want to show you a prompt example that we can send to our DApp to generate the image. Here we are using this pixel sprite before the prompt because it's part of the model that we are using. Let me just check if I put this here. No, of course this part of the pixel sprite could be in the code for the user do not have to type it. Is an improvement that I will be making in the future that it's easily done. Okay, I just do not want her to alter this code as I record the video, of course, so things do not go wrong, but it's a simple fix. um, the steps that we are using, so the steps like the stable diffusion model, as you may know or may not. So if you already know, excuse me for the explanation, but just for everyone to understand, when we are dealing with the stable diffusion model, what is being done in simple terms is that you take an image, you are adding some noise to this image. So each step you will add a little bit of noise to the image until this image is pure noise. And we use the artificial intelligence to have noise, so we have a pure noise. With the prompt we are denoising this image to come to an image that matches this prompt. Okay, it's not exactly this that is happening, but this is a simple explanation so you can understand these steps. So in theory, of course, there is a threshold, but as you add more steps, you will have better images. Of course, uh, when you come to a number of steps, the image will not change further from that number. So like maybe 50 steps. If 51, 52, the image will be the same because it already achieved maximum. Um, so we have these other parameters like height and width. If you make this bigger, uh, you will take longer to generate the image, and if you use smaller ones, the image will not be good because the models are trained for generating images with this minimum height and width. So when you use below this, you don't get uh, satisfactory results. So this would be the minimum recommended height and width. The sampling method that you're using, the number of threads, and some other stable diffusion parameters that you can check out for yourself in that repository or in other places of the internet. So here we have a prompt that may be the ones that you are most interested about right now. That is a lovely cat, and we are using this pixel art model. Okay. Um, so I believe the code. This is it. This is the huge part of the code. Um, and I will try to execute this right now for you. Here it was a test that I was making. Let me stop this. So as I told you, we are going to use NoNodal for this test so we can simulate the Cartesian environment. For using NoNodal, you have to initialize it and you have to export this environment variable that is the rollup HTTP server, okay? And in this specific case of the C++ code, you use this command. You make clean, make, and execute the app, okay? So here, right now, we have already our code executing, as you can see for the sending finish. That is the infinite loop that we have here in the code for receiving the advanced requests. And let me start a terminal here. And with the Cartesian send, we can send this advanced request to start generating our image, okay? Send input, foundry, okay, and the string encoding that we're going to use. Oh, sorry, guys. I had this in my Control C, but this is not what I wanted to use. Okay. Let's try again here. I have this example prompt, but I would like this without the break lines. Okay. Right. Just let me check if I copied right. Okay. So generic input, foundry, mnemonic, okay, stringing, and now I'm using this prompt as I told you, a lovely cat, and etc. And right now you can see here that we are using our terminal here. We are executing this command as the Mac with the model, the prompt, type, steps, height, width, sampling method. That is, as we are told in here, to execute the model. So it is loading the model, loading the stable diffusion. We are using, you can see, less than 2 GB of RAM. We are using UNet, Vi. So we are loading the model, we are running, and all of that good stuff. I believe that this will take in my MacBook. Remember that right now we are simulating the Cartesian environment, but we are using the power of the CPU of the MacBook. So this will take like 2 minutes, But this image, this exact image in the Cartesian machine, if we try to run this from Docker, I guess it would take like 50 to 60 hours, uh, maybe a little less, but something like that. More for days than minutes, okay? Uh, and I'll try to show you in the end of this video the results that I have achieved in the Cortez machine. I generated the simplest image possible that is not even an image, it's like noise, because I use like one step. Here we are using 8. Actually this parameter is like the bare minimum that you could use to generate a satisfactory image uh, using this model. Okay, I tried a lot, and this was the minimum possible parameters that I've encountered. Okay, but for the test I use like one step, like 64 to 64 image. As I told you, not good results, and it took like 12 hours in the Cortez machine to achieve a result. So here the image was generated. I will not be able to show you the beginning of the logs here, because what happened was the image was generated. Here you can see the image here. I will show you this lovely cat that we have generated in the pixel art style. But what the code did was that this image was transformed into base 64, and this base 64 was encoded into hexadecimal, and this hexadecimal was sent as a report in the Cartesian environment. And actually we can check this out here, because we can use this, sorry, not here, here we have this GraphQL uh, tool offered by Cartesi. Okay, so this is also running in this case with Nonodo, but with if you were using the Docker, it would be working in the same way. This is just a query for us to get the reports, and here you can see the report with index 0 in the payload. Here you can see that is a big hexadecimal, okay, because it's not a small image, right? So let me copy this. Just a moment. It's not easy to copy this, but we will get there. I want to show you guys something. As I told you, this is a hexadecimal encoded representation of our image. So this is actually the image, but the image in letters and numbers, right? So we can go here in this hex to string. Here we have actually the string representation that we could imagine as the base 64 representation of the image actually. So this is the base 64, and here we have other converter that is base 64 to PNG. Okay, so let me paste here the code, and let's decode this. When we decode, we get to our lovely cat. Okay, so this was how we can run stable diffusion models, decentralized stable diffusion models, using the Cartesian machine to achieve this result. As I told you, to generate this pretty looking lovely cat, it would take like days. But this is some further first steps in running fully decentralized stable diffusion models. So I believe we have something pretty notable here. It was a long journey to achieve this result. It was not easy. We went further and back many times, as I told you. we tried using Python, then Rust, then C, then Python again, then C++. So I know the code is simple. I showed you all of the code. It's nothing of the other world. But when we are dealing with the Cartesian machine, with the Cartesian rollups, that we have all this uh, proprietary code of the Cartesian that is available. You can clone the repo, right? You can check the all the code that is the Docker Compose code, the health checks. But to understand all of this and change these variables for such an extreme case as this, I believe it was one of the biggest challenges that we've encountered. Uh, but we had all the support of the Cortez team uh, during this process. I believe that you guys, with all of these, you can clone my repo. You can try to make improvements that maybe in this period of time was not able. But this is a first cool step, I believe. And this is it, guys. I hope you have enjoyed. If you have any comments on this, please let me know. And oh, I will have to show you the results that I told you that I was going to show you guys. So just a second, right? So guys, um, I've sum up here the results that I've achieved when I was running this inside the Cortez machine using Docker here in my machine. As you can see here, I'm using the Cortez Docker Compose. I started the machine here and I received the request. Here you can see that I have some logs that I was executing the prompt. So you can check here, I choose one step, 64 with height and 64 width. You can see here some logs of the image being generated. Around 2 gigas of RAM. And you can see here that one step took like 1500 seconds for one iteration. This in my Mac, one step would take like 8 seconds. But this whole process take around 12 hours because we have the generating image time, but we have also to decode it. We have some steps further than this that also take a long time. You can see here to get learn condition took this amount of milliseconds. That is also a considerable time. You can see here the sending report, so the payload with the hexadecimal. Some other part of the logs, so generating one latent image, decoding it, take 2000 seconds, as you can see. We have also this. The whole text to image was complete in 5000 seconds. We have the result image saved in this directory. Here I was checking the reports and decoding the image. You can see that this was the image that was generated in 12 hours. The prompt, I believe, was also a lovely cat. This is the name of the model, okay, that I was using, the pixel model. And this was the image, but all the image that you generate that is not at least 512 by 512 will be something like that, because this is what the stable diffusion model generates for images smaller than that size. But as you can see here, all the code was executed. It took 12 hours, but with some more hours, we could have achieved better results, as I showed you using no nodal. Um, so I believe this is a first step to our goals. And I leave you with this so you can try to improve it for yourself. As I told you, you can call me, you can reach me. And this is it, guys. I hope you have enjoyed. Bye.